I want to start with a brief reminder of what we're doing. And then the goal of this lesson is to write a theorem which says precisely how to do the procedure that we exhibited in the example that we just did. So we're starting with a linear map, a linear operator, T, and a vector V, a non-zero vector V, satisfying that T on that vector, all it does is multiply it by a scalar alpha, so T of V equals alpha V. Such a special vector is called an eigenvector, a self-vector of T, it's a property of T, of V and T. So a special vector V, a non-zero vector V, such that T of V equals some scalar times V is called an eigenvector, and that scalar alpha is called an eigenvalue of T. And alpha and V go together, an eigenvector and a corresponding eigenvalue. If the space V has a basis which is comprised entirely of eigenvectors of T, okay, so this is a basis of the space V comprised of eigenvectors of T, then when we construct the matrix representation of T with respect to that basis, what we get, the way to construct a matrix representation is to let T operate on each of the basis elements. And since they're all eigenvectors, T of V1 is alpha 1 V1, T of V2 is alpha 2 V2, all the way up to T of Vn is alpha n Vn, and I'm omitting here all the 0 times the others, right? When I'm saying that T of V2 is alpha 2 V2, what it means is that T of V2 is 0 V1 plus alpha 2 V2 plus 0 V3 plus 0 V4 plus 0 V5 all the way to plus 0 Vn. So there's a whole bunch of zeros here that I'm not writing, and all that remains is these components in each of their images. And when we take the matrix of the coefficients, the transpose, what we get is this diagonal matrix. That's the matrix representation of the map T with respect to the basis B of eigenvectors. So if, and there's an if here, if the space has a basis of T eigenvectors, then T has a matrix representation which is a diagonal matrix. Such a T is called diagonalizable. So that's the framework in which we're working. Now, we did an example, a 2x2 example, a 2x2 matrix that defines a linear map, and we saw how we find the eigenvalues and their corresponding eigenvectors. And what I'm going to write now is just a theorem that says this, what we did in the example is precisely what we do in general. So let's write the theorem. So, before the theorem, I want to just say formally one thing that we said informally. So if T, so you can call this a definition. Suppose T from V to V is linear. So we have a linear operator. We define the determinant of T, the determinant of the operator, to be the determinant of the matrix, which is a matrix representation of T with respect to some basis F. Okay? So the first thing we have to do for this definition is to verify that it makes sense. So what do we mean by it makes sense? The notion of a determinant was defined for a matrix. When we have a matrix, a square matrix, we know how to find its determinant, right? It's a formula that involves the entries of the matrix. So now we have a map, an operator. The determinant of an operator a priori doesn't compile, right? It's not a matrix. But we're defining it to be take the matrix representation of the operator, take its determinant, define that to be the determinant of t. So first of all, it makes sense. But that's not sufficient. For a definition to be a good definition, we need to also verify that it is what's called well-defined. What do I mean by well-defined? I mean, and we mentioned this before, so I'm saying take t, take your favorite basis f for v, and then take the matrix representation with respect to that basis f. And then find the determinant. Again, a priori, it seems like the answer you'll get here, the determinant that you'll get, would depend on which basis you chose. Okay? And that would make this not well defined, because one person would take one basis and get a certain determinant for the map, and another person would take a different basis and get a different matrix representation and get a different determinant. Okay? But as we mentioned earlier, that's not the case, because if you take different bases, and it doesn't matter which basis you take, the different matrix representations, and they're going to be different, but they're all similar. That's the definition of similar. Different matrix representations of the same map are similar. Once they're similar, one of the properties of similar maps is that one of the properties of similar matrices representing the same map is that they share the same determinant. Okay? So this definition is independent of the choice of f. Let's remark this. Remark. The determinant of t does not depend on the choice of the basis f for v, with respect to which we find the matrix representation of t, since any two matrix representations, let's just write it, any two matrix representations of t are similar by definition, and thus have the same determinant. Okay? And therefore we say that this definition is well defined. Okay, questions up to here? So we're going to write stuff like the determinant of a map, and it makes perfect sense. Likewise, we're going to write stuff like, I'm not going to state it as a formal definition, we will write kernel of a matrix and just mean the null space of the matrix. Okay? All the elements that the matrix performing as an operator sends to 0. Okay? Ker A for all v's such that if we define T of v to be AV, then AV equals 0. Those are precisely the elements in the kernel of the operator defined by A. Okay? And if T is a map and A is its matrix representation, then the kernel of A and the kernel of T are the same thing. Right? Okay. So these are the two remarks that I wanted to clarify before we write the theorem, and now let's write the theorem. So everybody good? Everything falling in place, making sense? Okay. So I hope you remember at least the ideas that were in the example that we did previously, because that's precisely what I'm going to write. So the framework is again T from V to V, linear. a linear operator. And here are the parts of the theorem. The eigenvalues, the alphas, the eigenvalues of T are the roots of the polynomial determinant of T minus alpha I. Okay? And remember what we said. T is an operator. I here is the identity operator. So their difference, T minus alpha I, this is again an operator. What we mean by the matrix, by the determinant of this, is what we just defined. Okay? Take a matrix representation, look at the determinant of that matrix representation. Okay? So the determinant of an operator makes sense. Now, this operator, once you take a matrix representation, and it doesn't matter which matrix representation you choose, what you get here is a bunch of numbers, but there's still this alpha, right? So alpha here is a parameter, okay? And when you take the determinant, what you're going to get is a polynomial in alpha, just like in the example. So what's written here, although it doesn't look like a polynomial, is in fact a polynomial in the variable alpha. And do you remember what it's called?
Characteristic.
Right. The characteristic polynomial are the roots of the polynomial T minus alpha I, called the characteristic polynomial. Polynomial of T. Okay? Maybe we'll underline this because I don't think we actually defined it formally until now. So this definition becomes now part of the theorem. So that's the first part. This is how we find eigenvalues. We write down what is the characteristic polynomial and find its roots. Okay. 2, the second part. If alpha is an eigenvalue, so suppose we found such a root, such an alpha. So if alpha is an eigenvalue, then its corresponding eigenvectors those vectors such that T of V equals alpha V for this specific alpha are the non-zero elements, the non-zero vectors in the kernel of T minus alpha I. Okay? Again, this is precisely what we did in the example, right? For each alpha, we plugged it into this matrix, okay? And we solved the homogeneous system of equations that this is the coefficient matrix for, okay? So solving the homogeneous system is finding the solutions to the homogeneous system. The solutions to a homogeneous system are precisely those vectors that are sent to 0, are precisely the kernel of the system. And again, there's a blur here between the matrix A and the matrix representation A and the map. Okay? Okay. Okay. Maybe we'll prove these two first and then state a couple more statements separately. Let's add, before we prove it, let's add a couple of remarks. So remarks. So the first remark is the exact, or, well, it wouldn't be exact. an analogous theorem can be written for a matrix A. What do I mean? What do I mean? Let's look at the theorem again. This theorem starts with take a linear map. Okay? And for the map, we're saying what are the eigenvalues of the map, and what is the characteristic polynomial of the map, and what are the eigenvectors of the map. Okay? These words, eigenvalues and eigenvectors and characteristic polynomial and kernel and everything here relates exactly not exactly again, in a similar way to matrices. Okay? What do I mean? Start with a matrix, a square matrix, n by n. Okay? The eigenvalues of the matrix are the roots of the polynomial a minus alpha I, called the characteristic polynomial of the matrix. Okay? And it makes perfect sense. And if alpha is an eigenvalue, namely an eigenvalue is just an eigenvector or an alpha and a v such that a times v equals alpha v, just like for a map. Just like the map corresponding to the matrix. Okay? So if alpha is an eigenvalue of a matrix, then its corresponding eigenvectors are the non-zero vectors in the kernel of a minus alpha I. So everything makes perfect sense, and in the examples, this is actually what we did. Okay? And the words are used as freely, really freely, for maps and for matrices because we really identify them. We really think of a map as a matrix and a matrix as a map. Okay, good? So that's this first remark. An analogous theorem can be written for A. Analogous with all the definitions involved. Another remark, so this would be remark 1. Remark number 2, the set of all eigenvectors corresponding to a specific alpha, corresponding to an eigenvalue alpha. So you take an alpha, an eigenvalue, and you look at all the v's that are eigenvectors with this eigenvalue. So fix an alpha, look at all the v's that satisfy t of v equals this alpha v. The claim is, this remark is saying that the set of all these eigenvectors, together with 0, the 0 vector, is a subspace of V. Okay? Now, why is this a remark and not a theorem? In order to prove that something is a subspace, well, here it's a subspace of a bigger space, so what we need to show is that it satisfies the three properties of that 0 is there. Well, it's there because we took it. We need to show that it's closed under sums and under products by a scalar, right? But what I'm claiming here is that this is an immediate statement. You don't need to actually verify it. And the reason is the theorem. The theorem says that if you take an eigenvalue, what are all the eigenvectors corresponding to it? Let's look at the theorem. That's part 2 of the theorem. If alpha is an eigenvalue, the corresponding eigenvectors are non-zero vectors in this kernel. So it's some kernel. A kernel of a map is always a subspace of the domain. Remember that? Okay, so t minus alpha I is again a map from V to V. It's not t, it's a different map, but its kernel is still a subspace of V. That's a result that we know previously. Kernels are subspaces. So we took all the non-zero vectors, that's all the eigenvectors. When we throw 0 back in, we get the entire kernel, and a kernel is a subspace. So it's a direct corollary of part 2. Do you agree? So this statement is just a corollary of part 2. The set of all eigenvectors together with 0 is a subspace of V. Let's write, since it is a kernel. A kernel of something. It's ker something, therefore it's a subspace. Okay? And it has a name and it has notation. It is called the, give a wild guess.
The null space or something.
Well, not the null space, the word space is good, but what kind of space? It's a space of eigenvectors.
It's an eigenspace?
It's an eigenspace, that's what it's called. It is called the eigenspace of V corresponding to the map T and the value alpha. Okay, it is called, let's write, an eigenspace of T, and denoted, I don't know if this is completely standard notation, but that's how I'm going to denote it, V sub alpha. Okay, so for every eigenvalue, you get a different eigenspace. Okay, for every eigenvalue, you get a different collection of eigenvectors. They're all that kernel that we wrote, and therefore you get a different eigenspace. Good? Okay, so that's the second remark. Okay, let's prove the theorem. Okay, let's put a line here, because this is in fact another definition. Let's prove the theorem. So I want to prove two things. Let's look at the theorem again. I want to prove that the eigenvalues are the roots of this polynomial. And I want to prove that the eigenvectors are the elements of this kernel. Okay, that's what I want to prove. And in fact, the way I'm going to show it, 2 is going to emerge first and then 1. Okay, and it's going to be very simple, in fact. So let's write the proof. So I'm going to erase, let's start by erasing this board. Okay. So, proof of the theorem. So we need to first recall what is an eigenvector and what is an eigenvalue. But we just wrote that. So let's say that V, a non-zero vector, is an eigenvector if and only if, let's write this as a big long if and only if statement, if and only if T of V equals alpha V for some alpha. That's the meaning of being an eigenvector, right? Saying that T of V equals alpha V is the same thing. Again, it's if and only if T of V minus alpha V equals 0. Do you agree? Okay. Now that's if and only if. That's if and only if. I can rewrite this as T of V minus alpha I of V equals 0. I of V is just the map that does nothing, the identity map. So I of V is V for every V. Therefore, writing this is just is the same thing. Okay, but now I can rewrite this by the way we defined operations on linear maps. I can write this as T minus alpha I of V equals 0. Do you agree? So a vector, a non-zero vector is an eigenvector if and only if, pum pum pum, if and only if it satisfies this. What does it mean that t minus alpha I of v equals 0? It means that v is in the kernel of this map. So this is if and only if v belongs to the kernel. That's what a kernel means, of t minus alpha I. So a non-zero vector is an eigenvector if and only if v belongs to the kernel. Let's rewrite this so all the if and only ifs would be correct, because all of these statements should have v is not non-zero and v is non-zero and v is non-zero and. So let's rewrite it. Sorry. Let v be non-zero. V is an eigenvector if and only if, pom pom, if and only if and only if. Now all the statements are indeed if and only if, providing we're looking at a non-zero vector. So this proves part 2. The eigenvectors are precisely the non-zero elements of this kernel. That was part 2 of the theorem. Good? So this proves part 2. Good? Part 2 said if alpha is an eigenvalue, the corresponding eigenvectors are the non-zero elements here. Okay? Now let's prove part 1. So the question in part 1 is, what are the eigenvalues, right? Let's look at the theorem again. So part 2 we proved. If alpha is an eigenvalue, its corresponding eigenvectors, the v's, are the non-zero vectors here. This we proved. Now we're asking, what are the eigenvalues? So the eigenvalues are those alphas that admit such eigenvectors, right? That have some v's for which t of v equals alpha v, right? Meaning that the kernel here is non-zero, right? If the kernel here is only 0, then there is no non-zero element here. Therefore, there are no eigenvectors, and alpha is not an eigenvalue. Okay, so let's write that. So let's phrase it as follows. The kernel of t minus alpha I is not just the 0 vector. That's what it means that there are eigenvectors corresponding to alpha. If this kernel is just the 0 vector, then there are no non-zero vectors in it, and therefore there is no eigenvector for this specific alpha. Good? So we're asking, when is this kernel non-zero? When does it have v's that are not 0 vectors, meaning it has real eigenvectors? Okay? So this kernel is non-zero. What does it mean for a kernel to be non-zero? What does it translate to automatically?
Alpha is an eigenvalue.
What is not 1-to-1? Very good. No. A kernel of something is non-zero if the something is not 1-to-1. Good? Okay. So this kernel, so this proves 2. We put a period, and now we're starting the proof of part 1. The kernel of t minus alpha I is not 0 if and only if t minus alpha I, this map, is, if it's non-zero, is not 1-to-1. Do you agree? Okay. For a linear map, a linear map is 1-to-1 if and only if it is onto. Remember? So those properties coincide for a linear operator, right? So t minus alpha I is not 1-to-1, and hence, and thus, t minus alpha I is not invertible. And it's an if and only if. Okay, maybe we'll write not and thus is not one-to-one, i.e., it's not invertible. Okay, so this kernel has non-zero vectors, has eigenvectors, if and only if this map is not invertible. Okay, when is the map not invertible? If and only if its matrix representation is a non-invertible matrix, right? This is a theorem that we had. The map is invertible if and only if the matrix is invertible. And moreover, we know how to find the matrix representation of the inverse, right? Remember that statement? The matrix representation of T inverse is A inverse. Remember that? So there's a correlation between maps and matrices. Okay? So saying that T minus alpha I is not invertible is the same as saying that, i.e., when is a matrix not invertible? We had a bunch of equivalent statements to saying that a matrix is not invertible. Remember? There was one saying that for every b there is a solution, when it is invertible, for every b there is a solution to ax equals b. There was a statement about the rank, there was a statement about the determinant, there were a bunch of statements, and the one we're interested now is the one about the determinant, i.e., the determinant of this map. And again, a determinant, we can think of the determinant of a matrix representation, it's the same thing. So this determinant, it's not invertible if the determinant is 0. Good? So there are eigenvectors corresponding to alpha if this determinant is 0. Good? And that proves part 1. That's all we wanted to say. Those alphas that admit eigenvectors, those alphas that are eigenvalues, are precisely the roots of this polynomial. Alphas that satisfy the determinant of t minus alpha I equals 0. Okay, so this proves 1. Good. It's theoretic. Note how short this is, right? This is not for extracting this from the simple 2x2 example took us quite a while, right? But once you have the ideas, spelling them out abstractly is in fact rather straightforward. Good? Everybody good? Okay, so this proves 1. 1 said the eigenvalues are the roots of this polynomial. We agree that this is a polynomial in alpha, the determinant of t minus alpha I, and what we just found is that alpha admits eigenvectors and therefore is an eigenvalue if this determinant is 0. Therefore, if it's a root of this polynomial. Good? Everybody good? So back to the proof. I forgot one thing, which is to add the Halmash here. Okay? And what I want to do is to do another example. I want to do a 3x3 example, which is more complicated because it's 3x3 rather than 2x2. So verifying, calculating this determinant and finding this kernel are all going to be 3x3 issues rather than 2x2 issues, and therefore a bit longer. But I'm not going to trace that example carefully in order to extract the theorem. I already know the theorem. I'm just going to do this and do this. That's how we do it, right? That I want to do separately in a separate clip. Before that, I want to write another theorem which collects a bit more facts that we already encountered, okay, that we already know from the 2x2 example. And again, we're going to verify them on the 3x3 example as well. Okay, so here goes a couple more statements. And again, we're still in this abstract realm. I know once things get abstract, they get slightly more challenging than in the concrete examples, but really the way to grasp this well is to read it in parallel to the example. See that what we're writing, everything we're writing, is precisely what we did in that baby 2x2 example. Okay? So let's write the other two facts that we already know from the example. And those facts were, the first one was that if we take different alphas, then their corresponding v's are always linearly independent. Remember that statement? So that I want to prove. And the other statement was, if we take the matrix P, which is constructed by taking the v's, the eigenvectors as columns, that P is precisely the P that gives the similarity, the P that satisfies D equals P inverse AP. Okay, so those are the two facts that I want to write down now and give and outline the proofs. I don't know if I'll do them in full detail, but at least outline them. So here's the first theorem. Eigenvectors corresponding to different eigenvalues are linearly independent. That's the first statement. The proof is rather straightforward. It's going to be based on induction, on mathematical induction. Here's the proof. So we need to start with a collection of eigenvalues and eigenvectors. So let alpha 1, alpha 2, ... alpha k be different, and this is emphasized here. Okay, we're assuming that we're looking at different eigenvalues. If you take two of these to be the same, the statement is no longer true. Okay, so this statement is only valid if you take different eigenvalues. And let v1, v2, ... vk be corresponding eigenvectors. So T of v1 is alpha 1, v1. T of v17 is alpha 17, v17. Okay, they go in pairs. An eigenvalue with its corresponding eigenvector. We want to show that v1 to vk, that this set is linearly independent. That's the assertion of the theorem. Okay, and we want to prove it by induction. Okay, so we will show by induction that v1 ... vk, this set is linearly independent. Okay, so how do we execute induction? We start with the base case. Then we have the induction hypothesis on which we base the induction step, right? So what is the base case? The base case is k equals 1, right? K equals 1. If k equals 1, we have one eigenvalue. We have one eigenvector. Is a set of just one vector a linearly independent set? You're doing this, I guess you mean yes, but you have to be a bit careful. If you take a set comprised of one vector, is it always linearly independent?
It's not zero.
if that vector is not 0, right? So suppose we have just one alpha and just one v, can that be v be 0? Answer, no. Why not?
Zero. Because if you multiply
One word starting with def, that's the definition. The definition of an eigenvector is a non-zero vector, right? Good? So k equals 1, if we have a set v1 is linearly independent, for a set of one vector to be linearly independent, all we need to say is that that vector is not 0, since v1 is not 0 as an eigenvector. By definition, an eigenvector is a non-zero vector satisfying t of v equals alpha v. Good? So the base case is indeed trivial here. Okay. Now let's do the hypothesis. So the hypothesis is going to be that if we have k minus 1 alphas and corresponding k's, then they are linearly independent. And then I'm going to throw in another eigenvalue different from all the rest and show that the set of k are linearly independent. Okay, so here's the induction step. So let's consider, how do we show that a set of k elements is linearly independent? By definition, I'm going to take a linear combination, assume it equals to 0, show that all the coefficients are 0. That's what it means to be linearly independent. Now, alphas are taken, right? So I'm going to take, and I need general coefficients, so I'm going to call them beta. So consider beta 1 v1 plus beta 2 v2 plus ... beta k vk equals 0. Suppose we have a linear combination of the vk's which is 0. If we can show that all the betas are 0, that means that the v's are linearly independent by definition. Good? So we're assuming beta 1 v1 all the way to beta k vk is 0. The first thing I want to do is multiply this by alpha 1. Okay, multiply this by alpha 1. So I get beta 1 alpha 1 v1 plus beta 2 alpha 1 v1 plus ... beta k alpha 1 vk, sorry, here it's v2. So I just took this and multiplied it by alpha 1. Therefore, and I threw the alpha 1, I distributed it on all the components, and it still equals 0, because it's alpha 1 times 0. Sorry, it still equals 0. Do you agree? Okay. On the other hand, I'm going to take this and do something separate to it. So on the one hand, I have this. On the other hand, and now we're going to need another board. So on the other hand, what is t of this linear combination? Beta 1 v1 plus beta k vk. That's the linear combination. We're assuming that it's 0, right? So on the one hand, this equals t of 0, because we took a linear combination that is 0, right? And what is t of 0? 0 for any linear map. This is something we proved from the definition. T of 0 is always 0. So 0 equals t of 0 equals t of this linear combination, and t of a linear combination is the linear combination of the t's. right? So this equals beta 1 t of v1 plus dot 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 beta k t of vk. Do you agree? Right? This is the property of T being a linear map. Everybody good? Okay. Now what is T of V1? It's alpha 1 V1, right? We're assuming that these V's are eigenvectors corresponding to the eigenvalues alpha 1 up to alpha k. So therefore, this is what's written here is the same thing as beta 1 alpha 1 V1. T of V1 is alpha 1 V1. And T of V2, so we have beta 2, T of V2, so it's alpha 2 V2. Plus dot 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 beta k alpha k vk. And this equals to 0. Do you agree? Okay. So, and this is simply because these are eigenvalues and eigenvectors. Good? So on the one hand, we have this. And on the other hand, I'm going to copy the bottom row from the previous board that said that beta 1 alpha 1 v1 plus beta 2 alpha 1 v2 plus dot 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 plus beta k alpha 1 vk equals 0. This we obtain just by taking this linear combination and multiplying it by alpha 1. Okay, so we have these two statements. I'm going to subtract them. Okay, so what do I get? Okay, so this follows from this. This we know from earlier. Recall. So by subtracting we get, when we subtract the first component, they're equal and therefore it disappears. For the rest of them, tell me if you agree, beta 2, and here we have alpha 2 minus alpha 1 v2 plus, and here we're going to have beta 3 alpha 3 minus alpha 1 v3 plus dot 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 all the way up to beta k alpha k minus alpha 1 vk, and all of this sum equals, add a space, alpha k minus alpha 1 vk, and all of this equals 0. Do you agree? Good? Okay. Now look what we have here. We have some linear combination of k minus 1 vectors, v2 up to vk. A linear combination of k minus 1 of these, which equals to 0. By the induction hypothesis, v2 up to vk are linearly independent, right? The induction hypothesis says if you take k minus 1 of them, you're good. Prove it for k, right? That's how we do induction. So by the induction hypothesis, we have that all these coefficients are 0. There are k minus 1 of these vectors. It's a linear combination that's 0. They're linearly independent. All the coefficients are 0. Good? So by the induction of hypothesis, all these coefficients, beta 2 times alpha 2 minus alpha 1 equals beta 3 times alpha 3 minus alpha 1 equals dot 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 equals beta k times alpha k minus alpha 1. And all of them are equal because they're all just 0. Good? These are numbers. These are now scalars. Alpha 2 and alpha 1 are different. We're looking at different eigenvalues. So alpha 2 minus alpha 1,
Never zero.
it's not 0. Very good. We don't know much about it, but we know it's not 0. So if this product is 0, this implies that beta 2 has to be 0. Alpha 3 and alpha 1 are different. So alpha 3 minus alpha 1 cannot be 0. So if this product is 0, beta 3 has to be 0, and so on. Okay? So we conclude that beta 2 equals beta 3 equals dot 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 equals beta k. All of them are 0. So we started with this linear combination that was 0, and we proved that beta 2 up to beta k are 0. Are we done?
We have the proof for one. So
Right, we need to prove that beta 1 is also 0. Right? We need to prove that if we take a linear combination that's 0, all the coefficients are 0. Well, almost all the coefficients are 0, but maybe beta 1 is not 0.
we prove
Okay.
that it is V1 is 0.
Very good. Okay, so let's write that. We need another board. Let's not take another board. Let's write it here. So we still need to prove that beta 1 is not 0. So let's plug all these zeros into this. Okay, we know that this linear combination is 0. That was where we started. Okay, all the beta k's starting from 2 are 0. So beta 1 v1 plus 0 v2 plus 0 v3 plus 0 v4 plus 0 vk equals 0. So that implies that beta 1 v1 equals 0. Do you agree? If this is 0, everything is 0 except for the first one, so the first one equals 0, right? So we have beta 1 v1 equals 0, and v1 as an eigenvector is not 0. Therefore, beta 1 has to be 0 as well. Since v1 is not the 0 vector. Good? So we started with a linear combination that's 0, and we proved that all the coefficients are 0, meaning they're linearly independent. Good? Everybody? Okay. So this proves the fact that eigenvectors corresponding to different eigenvalues are linearly independent. There's one more statement that I wanted to make in this theoretic, rather long discussion. One final statement. And I can see that you're getting a bit overwhelmed. So maybe I'll omit the proof. I'll look at the proof and see if it's crucial or not. I think it's not. It's really, it's rather straightforward, but maybe it's not even long enough to omit. Maybe it's just worth writing. Let's look at it a second. Okay, so the last theorem that I want to mention, again, something we said in relation to the example, but now I want to say it as a theorem. Let A be diagonalizable, not diagonalizable, and let B equals V1 up to Vn be a basis of eigenvectors with corresponding eigenvalues alpha 1 to alpha k. Then the matrix P, whose columns are the VI's. So I'm just taking these VI's, there are n of them, putting them as columns of a n by n matrix P. Okay? This is an n by n matrix, let's emphasize this, whose columns are the VI's, satisfies that it's the matrix that implements the diagonalization, the similarity of A to the diagonal matrix. So satisfies P inverse A P equals that diagonal matrix with the alpha i's across the diagonal. Okay? That's the statement. Okay? So when we start with, when we find the eigenvalues and eigenvectors, which is the procedure we usually do by the main theorem that we proved a few minutes ago, en route we find the eigenvectors. If we take them and set them as columns, we get precisely the matrix that gives you the diagonalization, gives you the similarity of A to the diagonal one, which we called D. Okay? Now let me take a look at the proof. It's just a bunch of indices. It's not really hard. Think you can bear with me for another 5 minutes to have the complete picture? Because the theorems in this, we're going to have a few more theorems later on, which I'm not going to prove. Okay? But these are really the main theorems. These are the main statements about this entire topic. Okay? So let's prove this as well and wrap this up with that proof. So I'm going to erase here. It's really just being careful with matrix multiplication. That's all there is to it. Okay, so here's the proof. Here's the proof. So we want to show that P inverse AP is that diagonal matrix. Okay? A similar statement, let's look at the theorem again. I want to prove that P inverse AP is this D. Equivalently, I can multiply both sides from the left with P. Okay? So if I multiply both sides from the left with P, an equivalent statement would be PP inverse would be I, would cancel. So if I prove that A times P equals this diagonal matrix with P here, that would be an equivalent statement. Do you agree? Okay, so that's what I'm going to prove.
Why did you use different indexes
For what?
for the alphas? You used alpha 1 through alpha k.
Oh, no, that's a typo. Thank you. Right. Over here, please correct. Look over here. I wrote alpha k, and it should go up to alpha n. Right? V1 to Vn, corresponding alpha 1 to alpha n. Those are precisely the diagonal elements of D. Thank you. Everybody fix that? Okay. So instead of proving P inverse AP equals D, I want to prove that AP equals PD. Okay? So we will show that AP equals P times this diagonal matrix. And that's the same thing. Do you agree? Okay? And the way to show it is going to be very simple. I'm going to calculate the left-hand side, calculate the right-hand side, see that I get the same thing. Okay? So let's start with the the right-hand side. So what is P times this alpha 1, alpha 2, dot, 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 alpha n, and zeros? What is this? So I have to write what P is in order to carry out this calculation. But I know what P is. P is the matrix that has the eigenvectors as its columns. Okay? So the first column is really the eigenvector v1. Okay? And I'm going to name its components v11, v21, v31, etc. Okay? So I'm going to write v11. Did I write it v1, v21, v11? I called it v12. v12, dot, 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 all the way up to v1n. So this thing, this column, is just the eigenvector v1. Do you agree? The second column of P is v2. So it's v21, v22, dot, 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 all the way up to v2n. Okay? This column is v2. That's what P is made of. Right? The columns are the eigenvectors. So here there's going to be a dot, 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 and the last column is going to be vn1, vn2, dot, 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 vnn. Good? Do you agree? That's P. That's the assumption. Take P to be eigenvectors as columns. Multiply this by this matrix, this diagonal one, A1, A2, dot, 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 alpha 1, alpha 2, all the way up to alpha n, and all the other entries are 0. Right? Let's see what we get when we do this multiplication. So what I'm writing down here is the right-hand side. Right-hand side. What do I get? So let's start multiplying. Okay? So I get v11 times alpha 1, the first entry in the product. v11 times alpha 1, and all the rest of this row is going to hit zeros in the multiplication. Do you agree? So I'm just going to get v11 times alpha 1. That's what's going to sit here. Alpha 1, v11. Do you agree? Good? What's going to be underneath it? Underneath it is going to be second row times first column. All these are going to hit zeros in the product. The only one that meets a non-zero entry is v12, which meets alpha 1. So I get alpha 1, v12. Dot, dot, dot. The last row times the first column. The only one that meets a non-zero, the only non-zero product in this sum is v alpha 1 times v1n. Do you agree? Let's go to the second column of the product. Second column is each of the rows times the second column in the diagonal matrix. And only the second entry in each row would hit the alpha 2, which is non-zero. So I'm going to get here alpha 2 v11, alpha 2 v22, alpha 2 v21, right? First row times second column. v21, it's alpha 2. Alpha 2 times v22, dot, 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 alpha 2 times v2n. Good? Dot, dot, dot. And the last column is going to be only these hit the alpha, hit alpha n. That's the only thing that survives. Good? All I'm doing is doing matrix multiplication. And by the way, we didn't do many proofs of this sort because they're abstract and scary. But in fact, these are, in a sense, the most straightforward ways of proving that two matrices are the same. This is just an equation of two matrices. We're claiming that they're the same. We're just writing what their entries are. Okay? So it's really an important way of proving. And in fact, a basic one. Okay? So what we get finally is alpha n vn1, alpha n vn2, dot, 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 alpha n vnn. Good? So what we got, and let me write it symbolically, this is precisely v1 multiplied by alpha. Do you agree? This column is just the eigenvector v1 multiplied by alpha 1. So what we got is alpha 1 v1, the vector, and I'm going to denote it like this. Okay, this is the vector alpha 1 v1 sitting in the, maybe we can write it in the middle. Okay, we have alpha 1 v1 sitting in the first column of this matrix. Do you agree? And the second column is alpha 2 v2. That's the second column of the product. All the way up to the last column is alpha n vn. Do you agree? That's what we get on the right-hand side. Okay, we get a matrix whose columns are just the corresponding alphas times the corresponding eigenvectors. Okay? Let's see what we get on the left-hand side and see that we get precisely the same thing. So let's write it here. Any questions so far? Is what we're doing clear? Sometimes people get very confused from such calculations, but just because they're abstract, because they're not numbers. But in fact, this is really a very routine, straightforward proof. Okay? So what is the left-hand side? The left-hand side of the equality that we're trying to prove holds is a times p. A times p, and we want to see that we get the same thing that we got for the right-hand side. So a times p is a times p. What is p? P is the matrix that has the v's as the eigenvectors as its columns. Let's write it using the same notation I just used. So its first column is v1, its second column is v2, and its nth column is vn. This is p. Okay, is it clear what I mean when I write something like this? Good? Okay. Now, tell me if you agree to this statement. My claim is that the first column of the product, I'm not even gonna write A explicitly as A11, A12, A13, etc. I'm going to leave it as such. And my claim is that the first column of this product is the vector A times V1. Do you agree? Okay, so how do I get the first column? I take separately each of the rows of A and multiply it by each of the columns. Sorry, how do I get the first column? I get each of the rows of A and multiply it by V1. Right? So the entire column is just A multiplied by V1. That's a vector. Do you agree? Is everybody with me? Does everybody agree to that? That's a key step here. If you can allow me to write this without breaking A explicitly into all its entries, it's much more illuminating than writing all the little entries. Good? Everybody with me? Okay. What's the second column? AV2. All the way up to AVN. Do you agree? Good? Now, what is AV1?
Alpha 1, V1.
Right. AV1, V1 is an eigenvector corresponding to the eigenvalue alpha 1. So AV1 is nothing but alpha 1 V1. And AV2 is alpha 2 V2. And AVN is alpha n Vn. Do you agree? Because these are eigenvectors and eigenvalues. Okay? So that's the left-hand side. AP is the matrix whose columns are the alpha I VI's. Okay? And this completes the proof. Both sides, we got the same thing. Look at the previous board. P times D, the right-hand side, was the same matrix. Good? Everybody? Okay. Okay, so I know this was pretty heavy, pretty long, but I hope not disencouraging. I hope you managed to trace all the ideas. And if you did get a bit lost, then what we're going to do next is precisely go back to the solid ground of an example, take a 3x3 example, and do precisely what the theorem says. Okay, let's recall the main theorem of this. The main theorem was this theorem that said, you want to find the eigenvalues? Look at this characteristic polynomial, the determinant of t minus alpha I, find its roots. Those are the eigenvalues. Once you have the eigenvalues, for each of them separately, find the kernel of t minus alpha I. Those are the eigenvectors. Okay? Once you have the eigenvalues and the eigenvectors, you can diagonalize, right? Put the alphas along the diagonal, that's your D. Put the vectors as columns, that's your P. Okay, good? So that's what we're going to do next after we take a short